Okay, so let's click on today. And this is after this talk, we want to take conference. Okay, so let's click on talk to see. The speaker of the second talk is William Chen from Illinois. And title of the talk is the non-congruence modular forms and fundamental groups of punctured curves.
All right, thank you. So thank you to the organizers for inviting me. It's really a pleasure to be amongst all of these experts here. Yeah, I guess, unfortunately, I feel like abelian geometry is not so popular in the US. So, but it's like really great to hear all these amazing results. Okay, so I'm going to talk about a relation between non-congruence modular forms and the arithmetic of fundamental groups of punctured elliptic curves. And in some sense, this reflects this idea that an elliptic curve, if you think of it as a genus 1 curve with a marked point, it's both an abelian variety, if you take that marked point as like the origin for the group law, but you can also view it as a puncture. You can remove the point and you get a hyperbolic curve, right? So it's both an abelian variety and kind of like an anabelian variety at the same time. And the abelian side kind of corresponds to the congruent subgroups of SL2Z, and then the anabelian side corresponds to the non-congruent subgroups. Okay, so let's just like begin with just recalling some of this congruence theory. So you have the group SL2Z acts on the upper half plane, and given a subgroup of SL2Z, you can have it act on the upper half plane as well, and then what you get is a modular curve, H mod gamma. Right. Okay. So associated to this subgroup, so this will be I'll always consider finite index subgroups. All subgroups I'll consider are finite index. So given such a subgroup, you can get this modular curve. It's a punctured Riemann surface. And you can also consider modular forms. So mk gamma, so this is the space of weight k modular forms for gamma. What does this mean? What is a modular form? You don't need to know too much about what a modular form is. It's basically a function, a holomorphic function on the upper half plane, and it satisfies some kind of transformation property with respect to gamma. So in particular, if it's weight zero modular form is actually it's actually fully invariant under gamma, and so it descends to a function on the modular curve, and then in general, for weight k modular form, it's not necessarily invariant, but it satisfies some kind of transformation property. Okay, so one aspect of these modular forms is that even though they're generally not fully invariant under gamma, they're periodic, and so they have a Q expansion, where a Q is e to the 2 pi I z. So maybe I should actually write n over w, because sometimes there'll be like ramification at the cusps, and so for some w at least 1. So for a modular form for SL2Z, it's really just they have a Q expansion an q to the n, where these an's are called the Fourier coefficients of f. Okay, so recall that a subgroup is congruence if gamma contains gamma n. So these are called the principal congruent subgroups, which is defined as the kernel of SL2Z to SL2Z mod n. Okay, for some n. Right. So basically what this says is that it's congruence if like membership in the subgroup can be detected by looking at congruence conditions on the coefficients of the matrices. Okay, so if gamma is congruence, so I'll recall some aspects of the congruence theory. So there's this theory of Hecke operators. So have a Hecke operators. What are Hecke operators? I won't go into them too much in detail, but basically there's some collection, it's an infinite collection of these correspondences on modular curves. So So what is a correspondence? A correspondence on a modular curve H mod gamma is just another curve with finite maps. These are finite maps to H mod gamma. And the idea is that whenever you have such a correspondence, yeah?
So I think you just take the period group 1 instead of SL2
Where?
So gamma n is just those matrices which are congruent to 1 modulo n.
That's right, yeah.
And so the group, so it's the kernel of a map which maps SL2Z to the group generated just by the
No, I think SL2Z mod n.
Okay. Okay. Yeah.
Yeah, it's the things that map in SL2Z that maps to the identity in SL2Z mod n. Yeah. Right. Okay, so you have these Heckel operators, and these are just some other curve with a finite maps to H mod gamma. And the idea is that, well, because this doesn't quite define a function from H mod gamma to itself, so it doesn't act as automorphisms, but whenever you have any kind of like linear object associated to H mod gamma, like cohomology or spaces of modular forms, you can basically pull back and then push forward, and this gives you endomorphisms on any of these kind of linear objects associated to these modular curves. So what you get is, I guess, this is a bold T, so this is called the Hecke algebra. So it's the Z algebra generated by this infinite collection of Hecke operators, and it acts on all of these kind of linear objects. So the spaces of modular forms, cohomology, homology, etc. Okay. And then you also have this kind of interesting construction where given F, let's say a weight, okay, 2 eigenform. So basically it's some special modular form of weight 2, which is a simultaneous eigenvector for the full Hecke algebra. So it turns out these things exist. So, and let's also say that it vanishes at the cusps of the modular curve, or of the upper half plane. And let's also assume that the Fourier coefficients are rational numbers. So it turns out that that's also not too restrictive of a condition. In particular, there are infinitely many such forms. Then given this, so you get a few nice properties. So it turns out that if they're all rational, they actually have to be integers. So all the Fourier coefficients have to be integers for this F. Secondly, you can do this, you can consider this construction where you just take the function on the upper half plane, right? And then you just like consider the function dz, where z is a coordinate on the upper half plane. And it turns out that, well, f of z, because it's not weight 0, it's weight 2, this is not fully invariant under gamma, but then when you also multiply it with dz, it turns out it's fully invariant under gamma. And so this defines a holomorphic differential on H mod gamma, on the modular curve, in fact, on the compactification as well. So it descends to a holomorphic differential on the compactified modular curve. And you can do this thing where you consider this quotient. So you can look at the Jacobian of H mod gamma. And you can quotient out by IF times the Jacobian, where IF is the ideal in the Hecke algebra vanishing, which kills F. Right. So we assume that F is like the simultaneous eigenvector for all elements of the Hecke, or for all the Hecke operators, and so you could look at you could look at the ideal in the Hecke algebra. It turns out that this is a commutative ring. You can look at the ideal in the Hecke algebra, which kills F. So with respect to which F has a 0 eigenvalue, and if you take the quotient by the Jacobian by this abelian subvariety, the result in this case is an elliptic curve over Q. And moreover, so this is the elliptic curve over Q. This is the elliptic curve cut out by this modular form. And moreover, so far, this is just like a complex analytic construction, right? You have this, function. You have these functions which are defined complex analytically, and it's like you assume that it's a simultaneous eigenvector for these Hecke operators. But amazingly, you get this arithmetic result where for all primes, AP of f, so this is the pth Fourier coefficient, is equal to 1 plus p minus the number of points on this elliptic curve over fp. So somehow the Fourier coefficients tell you something about the arithmetic of this elliptic curve associated to the this modular form f, right? So already this is quite this is quite an amazing construction, right? So I mean, this EF is constructed totally complex analytically from this modular form f, and then somehow there's still some relation between the Fourier coefficients and the arithmetic of f. And you can think of these AP of f's, right, as telling you something about the action of Frobenius on the abelian fundamental group of this EF, of this elliptic curve over Q.
So it's the final value. So we have to take a P to which E there. We have a good idea.
Oh yeah, sorry, right. So I mean, I'm leaving out some words, I guess. So for all P, yeah. So not dividing the conductor. Yeah, P not dividing NF, where NF is the conductor. Sorry, yeah, I could say NF, I guess it's like any prime not dividing the level of the modular form, which is the conductor, which is related to the conductor of the elliptic curve. And then technically maybe you want to take F to be like a modular form for gamma 1 of n instead of, okay, but I mean, I'm leaving out a lot of words here, but this is basically the idea. And 3, of course, there's this amazing, deep result. So the modularity theorem says that, in fact, this association that goes from F to EF is surjective. In fact, you could probably make this bijective if you kind of choose, describe what F's you take. Okay, so what happens if gamma is non-congruence? So it's a theorem that there are no, so there are no Hecke operators in the sense that, so it turns out that the way that you define Hecke operators can also be defined for the definition works just as well for non-congruence subgroups, but it turns out that that definition basically acts on these modular forms in cohomology trivially. So you don't have an effective Hecke theory, and in fact, the Fourier coefficients for these non-congruence modular forms, in general, it's totally this property totally characterizes non-congruence modular forms. The Fourier coefficients of non-congruence modular forms have unbounded denominators. So if you normalize them so that the Fourier coefficients are all algebraic numbers, they will have unbounded denominators. And in fact, there's this unbounded denominator conjecture, which was recently proved, that says that you can recognize whether a modular form is congruence or non-congruence by this property. Okay, but on the other hand, here's the theorem that I'd like to describe. So let M11, so this is going to sound like a very particular case, and in a way it is, but that's because I guess the more general theorem has a lot of conditions, and this is kind of the nicest case. What are the nicest case? So let M11 be the Mathieu group. So this is a finite simple group of order 7920. And you can consider n, let's say np. So this will be defined to be the number of isomorphism classes of M11 covers of elliptic curves over fp only branched above the origin with ramification index 3. Okay. So for every prime, you can consider this set. So here I mean M basically covers which are Galois with Galois group M11. And so for every prime, you can consider this set of covers, and you let NP just be the number of different isomorphism classes of these covers. Then there exists a non-congruence modular form f, which let's write it as a n q to the n, whose Fourier coefficients a n determine for all p not dividing some analog of the level, which is 7920 in this case. It's the order of the Mathieu group. So you avoid, as long as you avoid these primes, which determine for all this NP. Okay, maybe I should have said which determine NP for all P not dividing this. That's a better way to say it. Okay, at least up to plus or minus some universal constant C can take. C isn't too big. You can plus or minus 12 basically. But the point is that this C does not depend on P, right? So even for very, very large P, you can basically count the number of M11 covers, right? So basically this is saying that the Fourier coefficients there's some non-congruence modular form whose Fourier coefficients basically count points on some Hurwitz space, right, of M11 covers of elliptic curves. And you can think of this as just like knowing these APs, right, tells you something about the action of Frobenius on the abelian fundamental group of this elliptic curve EF down here. You can think of this as saying that somehow F encodes information about the Frobenius action acting on the fundamental groups of punctured elliptic curves over FP. And well, I could leave it as that. It gives you some information about the action of Frobenius. More precisely, it gives you action about the kind of the maximal pro M11 quotient, right, of these fundamental groups. So the maximal pro M11 quotient, this is just defined to be the maximal quotient, all of whose, the maximal quotient, all of whose like finite composition factors are M11. This is also just a direct product of some large, very large number of copies of M11. Okay, so let's see. So I started at 11:15, right? I think. Okay, great. Okay, so what now? So I guess I'll just describe first these Hurwitz spaces, how they're related to non-congruence modular forms, and then eventually I'll describe how to prove this theorem. And I guess along the way I'll also mention some like fundamental questions that come up, which are not entirely related, but also of interest. Okay, so let G be a finite group. Okay, so it'll turn out that we'll only want to consider finite two generated groups, but then if G is not two generated, everything will be trivial, so it's not too bad. Okay, so let M or HG, so this is going to be the Hurwitz space of covers of elliptic curves, which are G Galois only branched above the origin. Right, so I'm just going to write it as a set, but it's a moduli stack of G covers of elliptic curves. Okay, so let's fix some elliptic curve over Q. And so what do these moduli stacks look like? So let me just recall the general picture. So the picture is, okay, so you have a forgetful map from HG to M11. It just forgets the cover and just gives you an elliptic curve. And this is a finite étale. So here, you can assume, for simplicity, you can just think that everything is over C, and in fact, I'll just write everything here. You can kind of just assume that everything is over C, but this also works just as well over Z adjoined 1 over the order of G. So at any prime which doesn't divide the order of G, everything basically is still good. In particular, this map is still finite étale. Okay, so this elliptic curve, this chosen elliptic curve, gives you a point, right? You can think of it as giving you a geometric point.
But if it is abelian,
then
then it is empty. So empty
Oh, well, only, okay, so only allows not branched. When I say only, I also allow for unbranched. Yeah. So at most branched. Yeah. Okay, yeah. Yeah. Only branched at most. At most branch above. Oh, okay. Okay, so you have this forgetful map, right? And you can look at, given a geometric point, so this is finite étale, so to understand this Hurwitz stack, it suffices to understand, well, the monodromy action of the fundamental group of M11 on a fiber. What is the fiber above this point? Well, by definition, because this is a forgetful map, the fiber above this point is just this isomorphism classes of G covers, right, on this particular elliptic curve. So this is in bijection with the, okay, so let me define pi will be just the fundamental group of, this will be the topological fundamental group, just to keep things simple. So this is a free group of rank 2. So this will just be the set of surjections from pi to G up to conjugation. Okay, so that's the fiber. So what is the fundamental group down here? So the fundamental group down here is classically well known to be SL2Z, but then this turns out also to be isomorphic to the outer automorphism group of pi, where the plus means that it's got determinant 1. It acts with determinant 1 on the abelianization, so corresponding to SL2Z versus GL2Z. So it's the pi 1 downstairs is this. Okay, so once you have this, now you have, well, on this fiber, you have to ask, what is the monodromy action, right? Well, on this set, there's kind of like an obvious action of out plus pi, just by precomposition. And it turns out that that is the monodromy action. Okay, so, so what does this imply? This implies that HG, these Hurwitz stacks, it's a big disjoint union. So by the Galois correspondence, right, the components of HG will correspond to the orbits of out plus pi acting on this set. And what you'll get is the disjoint union over all of these surjections to G, I guess, orbit representatives of, okay, what is each component? Each component is going to be a quotient of the upper half plane by a certain finite index subgroup of SL2Z, which I'll call gamma phi. This gamma phi is just the stabilizer under this action, a stabilizer of phi under this action. Right. Okay. Yeah. This is just a discrete group. This is the topological fundamental group of the complex points of the punctured.
So does this case strict stack or something? Or what is the
This is just a set. So this is just a finite set, and this is a geometric fiber. So it's a finite, anything which is finite over Q bar is really just a disjoint union of points. Yeah. So it turns out that this disjoint union points is exactly in bijection with this finite set. Yeah. Okay, so these moduli stacks, right, they decompose into these Hurwitz stacks, they decompose into this disjoint union of these non-congruence modular curves. And so just to maybe give some examples, and to just recall some of the, I guess, numerology. So note, so for phi, so from pi to G, right? Let's say pi, well, let's give it generators. Let's say it's freely generated by A and B. So the ramification indices of the cover corresponding to phi is just the order, right, of phi of the commutator of A and B. Why is it the commutator? It's just because that, well, if you look at an elliptic curve, say it's obtained from a square by identifying edges, what makes the two generators commute? Well, it's just like this, it's the square. It's this like 2 cell in the middle. If you puncture it, it's no longer Z squared, but the free group on 2 generators. And if these are the 2 generators, then when you going around the puncture, it's like A, B, A inverse, and then B inverse, right, which is the commutator. So the commutator is like a small loop around the puncture. So the ramification indices of phi is just It's just the order of the image of the commutator under this monodromy map. So in particular, as Hoshi noted, that so unramified is the same as G being abelian, right? Which is also the same as the cover being also an elliptic curve. Okay, and let's see. We also have, so if G is abelian, we can again think about this monodromy action, right? What is, so we have epi pi G mod NG. If G is abelian, this is just, okay, you can replace the pi with its abelianization, Z squared G, right? And then the action of out plus pi will factor through the action of SL2Z. It's not really factoring through because, in fact, this is an isomorphism. But you can kind of understand the action through the action of SL2Z also acting naturally on this set. And so from this, you can observe that what are the stabilizers? Are congruence, right, if G is abelian. Why are they congruence? So just to give an example, e.g., the stabilizer of, let's say, the surjection that goes from pi to Z mod n squared, there's basically only one such surjection. And this stabilizer is exactly gamma of n, right? Because you're looking at the, well, any surjection from pi to this, where it factors through Z squared, so you're looking at surjections from Z squared to Z mod n squared, and then the stabilizer are those matrices in SL2Z, which induce the identity on Z mod n squared, which is to say that it maps to the identity in SL2 Z mod n. Okay. So, so there are some natural questions, or these are very fundamental questions. Without answering these questions, it's very hard to do anything with these moduli stacks. So the first question is, okay, so on the one hand, this kind of description already gives you a, okay, sorry, actually there's something else I should say before I go to these questions, which is which subgroups can appear. So in fact, here's a theorem of Asada, originally due to Asada, but also it was improved by Ellenberg and McReynolds. So this theorem basically says that SL2 Z hat, SL2, sorry, the profinite completion of SL2Z has the congruent subgroup property in the sense that, and what it means is the following. So every finite index subgroup of SL2Z contains gamma phi for some surjection, some phi from pi to G. Okay, so basically this means that the set of these gamma phis forms, this cofinal system inside the finite index subgroups of SL2Z. And so in particular, it tells you that basically every non-congruent subgroup kind of can be obtained from a construction of this sort, right? Okay, so the components of these Hurwitz spaces, as G varies over all finite groups, you really only want finite two generated groups. As G varies over all these finite two generated groups, the components of these Hurwitz spaces give you all non-congruent modular forms. In fact, it gives you all non-congruent subgroups of SL2Z. In fact, it gives you all finite index subgroups of SL2Z. Sorry? Yeah, for some G and phi, yeah. For some thing, for this whole thing, yeah.
Why are those called congruent? Where's the congruence? I've noticed always.
Oh, this congruent subgroup property?
Yeah.
So it comes from the fact that in general, if you have an automorphism group of any group, so aut of let's say H, right? You can define the notion of congruent subgroups for this thing. And the congruent subgroups are exactly the stabilizers, basically, of H.
The word congruence that interests me. I mean, you think it would have come from SL2 as a
Well, yeah, so I guess they had to come up with a name. My theory is that they had to come up with a name, and for SL2Z, you could say, well, this is, or sorry, just for SL2Z, you could say that the classical notion of congruent subgroups can be viewed as this being a subset of aught of Z squared, right? And then you could generalize this notion. So now you take aught subgroups, you take any automorphism group of any arbitrary group, and then, right, you have this more general notion. Yeah, I don't know. I don't really know why they came up with this thing. Yeah.
Sorry, just so the statement is that if you fix a G and its rejection phi from P to G, then you have this. So can this be specified to the classical congruent subgroups gamma n?
Yeah. So when G is Z mod n squared, you get gamma n. The stabilizers are gamma n.
So classical congruent subgroups are congruent subgroups, but not vice versa.
Correct. Yeah. So this is like a generalized version of congruent subgroup, and it comes from the fact that you have two notions of congruent subgroups via this isomorphism between SL2Z. This is quite an exceptional isomorphism between SL2Z and the outer automorphism group of free group of rank 2. Yeah. So you have like two notions of congruence subgroups inside the same group coming from this exceptional isomorphism. Yeah. Okay. Okay. So let's go to the questions. So questions. Okay. So the first one is, can you describe the connected components of these Hurwitz stacks, right? And it turns out this is so. Without you can get some like just general, like you can understand the degree of this full map, right, from HG to M11. Let's say, let's take like the maximally kind of non-trivial cases where G is like a finite simple group. Then you could describe the degree of the full map, right? The degree of this map, of the forgetful map, is just the size of this set. And the size of this set, I mean, you're basically counting generating pairs of finite simple groups, and there are lots of estimates. You can use some representation theory, and you can really understand. You can get some. It's hard to get like exact answers, but you can at least get pretty good estimates for the sizes of these sets, right? So, and you can also get pretty good estimates for like the ramification behavior, like how many ramified points are there. I mean, M11 is basically a curve, so this is basically like a disjoint union of curves mapping to M11. But this is all like kind of global. Right, and unfortunately, even with all this information, you could try to say, okay, like maybe if you want to understand the geometry of these HGs, well, to understand the geometry, ideally you'd like to understand the genus. One thing is, can you understand the genus of these HGs? Why would that be nice? Well, for example, if you could say that a certain component is genus at least 2, right? Then by Falting's theorem, this tells you something about the finiteness of G covers of elliptic curves defined over number fields, which is kind of it's already a type of a Abelian result, right? So that would be quite interesting. But you just can't access the genus, which is already kind of a coarse piece of information. You can't even access the genus without knowing the connected components, right? So okay, so the first question really is this like very basic question of understanding the connected components of these Hurwitz stacks. And so there's the simplest case is when G is abelian. So when G is abelian, this question is basically trivial. So in this case, pi 0, the connected components, they are in bijection with the set of generators. So here's one kind of slick way to write it: generators of the wedge product, the wedge square of just the exterior square of G. So if G is an abelian group, you can talk about the wedge square. And it turns out this will always be a cyclic group, and so you could talk about the set of generators, and the components are totally classified by the set of generators. When G is non-abelian, the situation is much more complicated, and in fact, there's only one even conjectural description of the set of components. So this is due to McCullough and Wanderley. I'm going to say 2013. And what they say is that pi 0, the set of connected components of the Hurwitz stack of SL2 FP covers of elliptic curves is classified, completely classified by the conjugacy class, so I'll just write class of the image of the commutator. Okay, so firstly, I guess you should check that this makes sense. I mean, moduli theoretically makes sense because every cover, right? For any cover, you can talk about the monodromy type of a small loop around the puncture, and you know, this is kind of like a discrete invariant. This is invariant under deformations, and so this should be like give you a discretely valued function on the Hurwitz space, and so for every value of this conjugacy class, you should be able to get some union, the corresponding subspace of HG is some union of components, right? And what this conjecture says is that, in fact, it's totally classified. So there's one component for every conjugacy class. Well, okay, what it says is that there's at most one component for every conjugacy class. There is like one or two conjugacy classes that can't appear. But
you mentioned the abelian case, but is this G a general abelian, or G is isomorphic Z modulo N2?
General two-generated abelian. Actually, it has to be two-generated because if it's not two-generated,
for example, cyclic group.
yeah. So then this would be trivial.
You mean
It'd be the trivial group.
you mean correct?
Huh?
In this case, this is correct.
Yes. Yes. That's right. There'll be only one component. Yeah. So this, I guess I say this, the set of generators of this trivial group is just identity. One. Okay. Right. So one theorem towards this is due to Bourgain, Gambard, Sarnak, and myself, which is that we basically prove this for a particular trace. So basically, in SL2FP, these conjugacy classes are totally classified they're essentially totally classified by the trace, with the exception of trace plus or minus 2, in which case there are like 3 conjugacy classes. And then it turns out that like for trace -2, negative of the identity cannot appear as the conjugacy class describing the monodromy around the branch point. And so there are only 2 possible conjugacy classes available for trace -2. And in fact, we show that this conjecture holds in that case. So there exists exactly 2 isomorphic components. Let's call them XP for trace -2. Okay. And this theorem requires quite a lot of work. Yeah, so Bourgain, Gambard, and Sarnak, they kind of get you almost all the way, and then I prove something that kind of gets you kind of even closer to the goal. But yeah, so this in general, it turns out that these types of questions, in terms of like understanding the set of connected components, it's very difficult, and it's kind of analogous to the question of classifying Galois orbits on descent enfant, right? Because you can think of the case where, you know, H03, right, is really just H. You could do the same thing with H03, and that maps to what, M03, which if you do this arithmetically, this is just spec Q, right? And classifying the connected components is just classifying the Galois orbits on descent enfant. Okay. No, just theorem. Yeah. Okay. And then just to illustrate like why, you know, it's what you can do once you have the components. Once you've described some of these components, you can show that also that the genus of these components is approximately, it's asymptotic to p squared, 1/12 p squared, and so in particular it grows, right? And this is not clear at all that it should grow as p grows. And so, for example, this implies that eventually it's at least 2, and so this implies finiteness of SL2 covers. Of finiteness of SL2 p covers of elliptic curves with ramification index 2p above the origin. Right? Turns out the trace of something being -2 basically means that the ramification basically means that that element has order 2p. And then also, again, also using this connectedness, you can also compute the monodromy groups. So you can get Mary Puder. They show that the monodromy of these xp's over M11, they're either alternating or symmetric on the degree. Right. So the monodromy groups are as big as possible. And in a way, this is kind of what you would expect for groups which are close to being finite simple. Sorry, this is a slight lie. By xp here, I'm going to put a prime here, where the prime corresponds to, you actually want to look at these moduli, the components for not SL2p, but PSL2p. And then what you get is that the components are alternating or symmetric. And from this, you can actually tell that these components are non-congruent. XP is non-congruence. It's actually a non-congruence modular curve, which is also a priori not at all clear. Okay. So, oh, you know what? I should have left this. Okay. So the next question is, when are the components congruence? And it turns out this is also a very subtle question. So you can do the general philosophy, which you can kind of develop and you can get a sense of by just computing lots of examples, right? For every finite group G, you can compute this set of surjections from this free group of rank 2 to G, and you can compute these orbits, and then from the orbits, you can compute kind of the genus and whether or not the stabilizers are congruent. And just by computing lots of examples, you can get the sense that if G is very non-abelian, you should expect the stabilizers to be non-congruent, right? And that's the general philosophy. But it's actually very hard to it's really very hard to like draw the line between when a group gives you non-congruence components versus congruence components. And to just give you some results towards this picture, so together with Lubotsky and Tiep, we show that, so if G is non-abelian finite simple, then there exists at least one element of, or at least one component, which is non-congruence. What you would expect is that all components are non-congruent. And this is in fact the case in almost all situations. However, there are situations where if G is PSU3 BFQ for let's say Q at least 4, I think that should be enough, then there exists one congruence component. Which is kind of totally surprising. In fact, you can see that there's basically only one congruence component, and then all the other components are non-congruence. And so what does that say? One way of interpreting this is that somehow, in this case, the theory of the Galois action on the abelian fundamental groups of elliptic curves tells you something about PSU3 FQ covers, right? Okay. So I'll just say that these come from the Borel representation of the braid group B4, and there's an exceptional relationship between the braid group B4 and elliptic curves. Actually, that was actually mentioned in, I think, Minamide's talk yesterday. Okay, and then before I actually, oh no, this one, no good. Okay, better. Okay, so before I describe the proof of the advertised theorem, let me just mention that, okay, so now you can also talk about when G is solvable, what happens, right? When G is solvable, it turns out that, so we know that if G is abelian, then all the components are congruent. It turns out that if G is metabelian, all components oh no, are also congruence. And in fact, you have a much stronger result. And in fact, there are a bunch of results that you can, there are a bunch of things you can say, which is that if you have, let's say, an elliptic curve over Q, then let M be the maximal pro-metabelian quotient of the punctured étale fundamental group. Then what you get is, okay, so you have so let's talk about, there are two monodromy actions you can talk about. You can talk about the monodromy action of the absolute Galois group, or the monodromy action of the mapping class group, and they're both a piece of this. Okay, okay, so let's put SL2Z hat here, right? This is the mapping class group, and then down here you have the absolute Galois group. These are both injections. The middle guy is the semi-direct product of the outer two. Okay, so firstly, you can look at the action on GL2Z hat, right? Which is the action on the abelian fundamental group of the elliptic curve, so of the non-punctured elliptic curve. And then you can look at the action on out of M, right? And it turns out there's a surjection here. And the theorem says that, in fact, there is a, so there exists a section. This surjection of groups is split. Okay, so there exists a section such that, so here's rho, the representation, the abelian representation, rho ab. Here's the metabelian representation, rho meta, such that image of rho meta is equal to the image of the section. Right. So in particular, it says that, so what does this say? This basically says that if you know how it acts on the abelian fundamental group, how either absolute Galois group or the mapping class group acts on the abelian fundamental group, then you know how it acts on the metabelian fundamental group. So in particular, the metabelian theory of punctured elliptic curves is not anabelian. Right? You could say that. Okay. So okay, so let me try to describe the theorem now. So modular forms. All right, so let me just begin by recalling a collection of facts. So there exists, this is great. Okay, there is a unique component, X, inside the set of, inside the Hurwitz stack of, let's take the compactified Hurwitz stack of M11 covers of elliptic curves, classifying covers with ramification index 3. And you just check this by computing the components, and it turns out that for ramification index 3, there's only one component. And okay, what do we know about this component? We know that X is genus 1, defined over Q, has an unramified cusp, right? So a cusp of width 1. Which basically means that there's a point at infinity which is unramified under its map to the J line. Okay, and good reduction at P any prime not dividing 7920, which is the order of the Mathieu group. Okay, so let omega be a holomorphic differential on this guy, on this modular curve, compactified modular curve. Let's assume you can always scale it so that omega is not 0 mod p, right? So it's not like, yeah. So let's just assume that it's not 0 mod p. Okay, then you can write omega as 2 pi I f dz, where f is a modular form, so a n q to the n is a modular form for gamma, where x is h mod gamma. It's the subgroup uniformizing x, this component. And it turns out that this gamma is non-congruence. Okay, so it is, non-congruence. Let me write that. Okay, so one thing you could do is you could let's replace this dz with dq, right? And when you replace it with dq, it turns out that this 2 pi I disappears, and you just get f dq over q, which is a n q to the n minus 1 dq. Okay. So now, turns out that these differentials have the Fourier coefficients of these differentials, they satisfy a certain congruence condition. What is this congruence condition? So here's a theorem, which I think in this case, it's due to Katz. Scholl also has a paper kind of generalizing these congruence conditions. These are called the Atkin and Swinnerton-Dyer congruences. These are from Scholl's papers from '85. So it's quite old, actually. So it says that ANP minus AP of x. Okay, what do I mean by AP of x? So x is an elliptic curve, right? So AP of x is p plus 1 minus the number of fp points of x. Okay, so ANP, this is a Fourier coefficient of a modular form, f. AP of x is this trace of Frobenius for acting on the cohomology of this elliptic curve x, times times n minus plus p n over p. This is congruent to 0 mod p to the order, the p-adic valuation of n plus 1. Okay. So you have these congruences between the Fourier coefficients, and these congruences critically use this guy, which is a trace of Frobenius, right, which tells you something about the fp points on x, which is a modular curve, which is a Hurwitz space describing M11 covers of elliptic curves. Right. Okay, so let's just assume this for now. And so if you just take this as a black box, so now you have to ask yourself, okay, so these congruences at face value, right? These congruences say that if you know the if you know the trace of Frobenius, if you know like the arithmetic of the modular curve, then it tells you something about the Fourier coefficients, right? And the question is, can you reverse that, right? Can you say that, do the Fourier coefficients actually tell you something about this AP of x, which is the trace of Frobenius acting on the cohomology of the modular curve? And the answer is yes. So it turns out that if AM, we're assuming that the coefficients, a and they're not all divisible by p, right? This was like the omega not equal to 0 mod p condition. So if you pick some coefficient which is not 0 mod p, so if am is not 0 mod p, then you just need to know 3 coefficients: am p cubed, am p to the 4, and am p to the 5 determine AP of x, right? And how do you show this? Basically, the way that you show this is by showing that, okay, so you basically consider, so proof, consider,
Excuse me?
yes?
So how do you define the n over p?
Okay, so there's a convention which just says that basically if n over p is not an integer, then it's 0. That's the general convention, yeah. Okay, so the proof basically says that consider, you basically want to consider am p to the r, right? And you want to consider these congruences for these Fourier coefficients, right? When n is, I guess, n equals m p to the r. And basically you ask yourself, okay, so as r increases, these congruences get stronger and stronger, right? And what you want is you want to show that this, what you want is that this, you want to show that this thing doesn't grow too fast p-adically, right? In terms of divisibility, in terms of p-adic valuation. So you want to show that this thing grows slower in p-adic valuation than sublinearly, basically, compared to, or not sublinearly, but slower than r. You know, as r increases, so basically what you show is that, in fact, as R increases, it turns out that this thing, the valuation of this, is basically bounded by R over 2. So it doesn't grow too fast, and that's the worst case. In fact, if this is in the ordinary case, if x is an ordinary elliptic curve, then this thing would actually be a p-adic unit, in which case everything's fine. But then if it's super singular, you can still show that these ANs don't grow too large p-adically, and that tells you that as you make n, as you make R larger and larger, right, these congruences really do get stronger and stronger in terms of telling you information about AP, right? And then you just need to know that there's this like Hasselbalch bound on these APs. It's like at most 2 root p or something. Okay, so that's the proof of the theorem. Maybe I'll describe where does this result of Katz and Schull come from, and okay, so the idea is this. So we have x is our modular curve, right? We view it has good reduction at p, so we view it as a modular curve, as a smooth projective curve over ZP. Okay, we know that it has a unramified cusp, and we'll use that actually. So we can use that unramified cusp. So at the cusp, at the unramified cusp, let's move it around so that the cusp is at infinity. At that unramified cusp, what's the uniformizer? Because it's unramified, J inverse is a uniformizer. So J inverse is Q plus O of Q squared, right? J is like 1 over Q plus higher order terms. J inverse, the inverse of the J invariant is Q plus O of Q squared. So you can look at a formal, okay, well, a priori, let's just look at J inverse. We can take the formal completion, so let's call this x hat, is this, right? You can take the formal completion of x, it's actually not really formal because we're just looking at the spec, but you take this, you kind of complete along the section, the cuspidal section given by J inverse, and then this thing is also sorry, this should be ZP, yep. This is also Z double bracket Q, just because J inverse is Q plus higher order terms, and all those higher order terms, all the coefficients are integral even, right? Okay, so you can write it this way. Okay, so this basically tells you, this kind of gives you an algebraic realization of this Q expansion map. So when you have such a thing, you can look at, so there's a very classic object called the algebraic de Rham cohomology of this smooth curve over ZP, right? And this, so right now we'll just take, I mean, it exists, it's a group, it's a abelian group. It has a map just by functoriality from, induced by basically the inclusion of x hat into x. It has a map into, okay, so I'm gonna call this the de Rham cohomology of x hat over ZP. So this is not really a totally standard object. So I need to define it. So I just defined this to be H1 of the complex, which is kind of almost the most naive thing you could think about, which is ZP double bracket Q with a D map to ZP double bracket Q DQ. Okay, so that's a definition, right? Okay, but what can you do with this definition? I guess let me just write this one more step, which is that this is just ZP double bracket Q DQ divided by D of ZP double bracket Q. Right? And the point is that because the coefficient ring is not a field, this is not 0. This group is not 0. And you could think about what does it mean for an element of this numerator to be 0 in this group. What it implies is that there has to be some congruence conditions on the coefficients. You know, it's hard to write down the conditions, but there are some congruence conditions on the coefficients. Okay, so at this point, what you can do is, so there is, the guy on the left is quite classical. This is the algebraic de Rham cohomology, and you can think of this as this guy. There's a just like the Étale cohomology has a canonical action by the absolute Galois group, right? Algebraic de Rham cohomology of something smooth over ZP has a special relationship with the crystalline cohomology of the special fiber over FP, and that relationship gives you a canonical action of a crystalline Frobenius. On this guy. Okay, and then it turns out that you can also get, the thing on the right is also sufficiently crystalline. It also has an action of a crystalline Frobenius. And this map is equivariant with respect to Frobenius. And then you just have to remember that, okay, well, the Frobenius acting on this, there are all these like comparison theorems. In this case, you have the Frobenius satisfies f squared minus ap x of f plus p is 0, acting on the left. And so that must also be true having it act on the right, right? But then it turns out you can compute the action of Frobenius on the right in terms of any lifting of Frobenius. So f acting here is really just obtained by sending q maps to, so you could choose, you can compute it by looking at q maps to q to the p. And that's a valid way of computing the action of this crystalline Frobenius on this group, which is a very explicit group, right? And then you just have to say, okay, so you've got this thing, it has to be 0. How does it act on the Q expansion? Well, it has to act, the output of this acting on some Q expansion must satisfy certain congruence conditions coming from this thing that you're modeling out by, right? And those congruence conditions basically give you this thing, right? Okay, so actually that's it. Yeah.